Then share the screen. Okay, so welcome everybody. This is CS402, Introduction to Logic for Computer Science. Let me first enable the chat box. Okay. And this is a 400 level course in computer science, which means that, the 400 means it's something between undergrad and graduate course. So in practice, what that means is I'm gonna expect you to be much more proactive in learning the course materials. And also the particular evaluation strategy that we're gonna adopt for this course is also gonna be more, in some sense, involved, or requires more kind of active participation from your side. Okay. So this is the course on the logic from the perspective of the computer science. So I'm gonna, today's lecture is going to I'm gonna give you some overview about this, the topic that we're gonna cover. Also at the same time, my plan is to give you, explain to you how we're gonna run this course and how we're gonna evaluate, how we're gonna give you marks at the end of the course. Okay. So let me start with some historical perspective on the logic. Okay, so I think the first question we have to ask when we start this course is what the title of the course means. Especially, the title of the course contains the word logic. I think most of you have some idea about what logic is about, but I think it's always good to go back to the origin and think about what the logic actually means and what people intend to say when they use the word logic in a principle like what we are covering in this course. So a good starting point is to look at the famous logicians, what famous logicians think about what logic means. So here's a quote by Tarski. I think most of you haven't heard about Tarski. He's a founder of one big branch of modern logic called model theory. And he's also regarded as the really great founders of modern logic. Okay, and he wrote a book on logics, maybe a book or an article. And in that, in his write-up, he gave a kind of definition of logic. He said, essentially what he said is, in multiple areas of science, there are some common things that's going on. People use some common terminologies, and then they adopt some method to manipulate these common concepts, which form the, in a sense, key meta methodology employed by multiple areas. And then he said that logic is about studying this meta methodology. And Frege, although he's a bit quite older than the Tarski, he's give a more precise comments about what Tarski actually meant. He said, if you look at the different science, different branches of science, such as biology, chemistry, and physics, and so on, although they study different phenomena, there are some common things that's really going on. They all try to discover the truth, and then, to discover the truth, they all employ some concepts that's related to the truth. More importantly, they all try to follow or try to exploit some rules that govern the truth. Okay? And then he said, the logic is not really about specific facts. It's more about the studying about these laws for the truth. And essentially, these two people are really saying logic is a study of principles behind the correct reasoning. Okay. So you can imagine that, lots of people from the ancient days, they thought this having some rules or some principles for the correct reasoning is important. So if you go back to the really old days about studies of the logic, we can stuff from Aristotle. So, I mean, I'm sure that you heard about Aristotle and Plato when you learn a course on philosophy. So Aristotle is, in a sense, a founder for many different areas of science, and I mean, not just science, but in maybe art as well as some other disciplines. So he wrote many books, and one of the book he wrote is about what we call syllogism. So some good way to understand this word syllogism is you can think of it as a pattern of correct reasoning. So it's a bunch of rules, and then each rule describe what would be considered as a correct examples of correct reasoning. So one of the syllogism is the one that you see on the screen. It say that all beings, the example of the syllogism is the one that you see on the screen. It says, if all beings are mortal and all humans are beings, from that we can deduce all humans are mortal. And this kind of deduction should be regarded as a correct examples of correct reasoning. More abstractly, you can view it as, what the Aristotle talk about is if all B are M and all H are B, then from there we can deduce all H are M. This is a kind of things that you immediately recognize as valid reasoning principle. And Aristotle collected all the, quite a few these correct reasoning principles. And then it turns out, according to what I heard, this was so influential so that like the next 1,000 years, people thought that, study about logic is done. That's what Aristotle did is a complete story about logic. So there was not much development about it. But around like 1500, and there was actually a movement about revisits these disciplines of logic and try to approach the study about logic from a different angle. And that's the time, maybe 1600 and 1700, that's the time where people developed calculus and then found that many things that we can say about in the real world, in other words, many phenomena that appears in the, that's the objects of study in physics, that can be analyzed using so-called calculus. So we can describe the phenomenon using equations, and then their derivative as well as integrations. And then in order to predict the future, all we have to do is to calculate. We compute the derivative or compute the integral that will give us, solve differential equations. So that will give us what's going to happen in maybe 10 minutes afterwards and so on. And then so that development motivated quite a few scientists at the time. The Leibniz, I think he's one of the founders of calculus. So many scientists at the time to do the same thing for logic. So what they thought was, they imagined a situation where if two persons argue each other and want to find who is correct, Leibniz want to provide a solution to them, in a sense, calculator for them. So if they use that calculator, they can write down what they are thinking, what they think is true. And instead of fighting who is correct, who is wrong, and they just do some calculation, and the calculation decide the winner of this discussion. That was the objective of that Leibniz and many others have at that time. So Leibniz kind of envisions a form of a calculus for logic. So he said, maybe we can come up with some formal language. In that language, we can write down a bunch of statements that we think is true. And then we also have a rules, some kind of calculation rules that manipulates characters or signs in the formal language. By using that language, we can write down what the kind of statements that we want to express, and then through the calculation, we can decide the correct statements. So that was the kind of vision of Leibniz. And then that vision was, pursued, but then I think the more concrete realization of the vision is done by George Boole. And what he did was he came up with something called a Boolean logic, and then he came up with equational rules for Boolean logic. And we're gonna cover his equational rules, and these equational rules can be understood as a calculation rules for statements expressed in so-called propositional logic. So some statement expressed in very limited form of this formal language called propositional logic. If two statements are written in that language, then we can use Boole's rules to decide whether these two statements say the same thing. In particular, this equational rules allows us to decide whether some statement is true or false. And in fact, these rules are very mechanical. So around the time Boole came up with his Boolean logic, or equational rules for propositional logic, some guy called Stanley Gibbons, he built some machine that implements the Boole's equational logic. So if you write down a statement in Gibbons machine and then run this machine, then that machine tells you what you say is true or what you say is false. Okay, so then that the study about the logic made various progress, but another big kind of change in the study of logic is the introduction of quantification. So around the 1900, not 900, the people worried a little bit about the foundation of mathematics. They thought maybe all these things that we do in the mathematics are nonsense because they are founded on, they are based on top of inconsistent set of rules. So what people wanted to do was they want to, in a sense, do the mathematical study about the mathematical foundations, the foundations of mathematics. So one outcome of this effort is what Frege and Peirce did independently, which is to introduce universal and existential quantification into the logic. Once you introduce universal and existential quantification into the logic, you can express many statements in, for instance, number theory, geometry, precisely in that language, and you start to think about, okay, what are the reasoning principles that we use when you do the day-to-day mathematics in a number theory and so on. So Frege and Peirce independently, they introduced quantification into the logic, and they developed essentially something called predicate logic. But it turns out doing so well is quite tricky. So I think many of you heard about so-called Russell's paradox. And Russell, when he looked at the Frege's Wright and Frege's work, he found that there is a inconsistency, or there is, the contradiction in the Frege's work. So this is something very well known. And then later, Russell wanted to fix this bug in the Frege's work. So what he did later is he, together with Whitehead, I think Whitehead was more like a hardcore mathematicians. Russell was at the boundary of philosophy and then in mathematics and so on. And they together launched a research program where they want to revisit what the Frege's work using some idea of types. And then they develop a new form of predicate logic and then develop mathematics, in particular set theory, analysis, and geometry on top of their version of predicate logic. So they did quite a bit of work, and then their works were published as Principia Mathematica. And what you see on the screen is, I heard this is a proof of 1 + 1 = 2 in their former system. So it's quite complex, but their objective is not to come up with kind of efficient proof system or efficient logic that allows you to prove 1 + 1 = 2 very quickly. instead their focus was more on laying the firm foundations foundations of mathematics, and which doesn't really have any contradictions inside. Okay. So the Russell and Whitehead works, and I think that that's when Russell and Whitehead did this work, that's the time lots of mathematicians were interested in the foundations of mathematics. So one of the big questions, so I think maybe you heard about the Hilbert problems. So I think that in the first international conference or international congress on mathematics, first or second, the David Hilbert, who was regarded as the kind of, giant of mathematics around that time. So Hilbert proposed multiple problems that essentially shaped the 20th century mathematics. And one of the problems was coming up with, in a sense, a logic which is consistent, so which doesn't have any contradiction, and also which can express all the things that we can do in the number theory. So that's what one of the problems of David Hilbert. And I heard like a very famous mathematicians like von Neumann and a bunch of others, they worked on this Hilbert problem. But it turns out, so, and then Russell and Whitehead works was around that time. So people were very much interested in laying the foundation of mathematics in a very firm ground. But around that time, what happened is that the one person from Austria, whose name is Kurt Gödel, he showed that this Hilbert question cannot be answered. It can only be answered negatively. That's because if we have a sufficiently strong logical system for arithmetic, in other words, sufficiently strong logical system for number theory, if the logical system is consistent, in other words, it doesn't have any contradiction inside, it cannot be complete. It cannot express all the truth. You cannot have rules that allows you to prove all the true statements in the logic, in the system. So this is called the Gödel's Incompleteness Theorem. And this was a big surprise to many mathematicians at that time. And I think it changed the research direction of, for instance, von Neumann. So it has a huge influence. But one possible kind of reaction to this Gödel's result is that maybe we can, I think maybe it's also one of the Hilbert problem, or maybe people revise Hilbert questions after this Gödel's discovery. I'm not entirely sure, but what people did afterwards is they revised their ambitions, their goal, and then said, instead of trying to come up with this kind of strong logical system that is consistent and complete, they fix a strong enough logical system. Then they change the question. They want to come up with a machine, a mechanical system that can produce, they can check whether statements expressed in this logical system is true or false. So both of these programs really kind of based on this ambition of making a solid foundation of mathematics, and then making mathematics as mechanical as possible. Okay, so they want to come up with a machine, essentially, that takes a logical statement, which express some statements in number theory, and then the machine can decide whether that statement is true or false. And they thought that much may be possible, because even in the presence of Gödel's theorem, because they are not really worrying about true statements about number theory. They are more worried about statements expressible in, which can be deducible or provable in this logical system. It turns out that toned down dream or toned down vision is also cannot be achieved. So Alonzo Church and Alan Turing independently show that there is no algorithm that decides whether a given logical system is, given logical argument is valid or not. So some statements which can be derivable in the which can be proved in some sufficiently powerful system. You cannot really have a machine that can show that that statement is derivable or not. So this church, proved this using lambda calculus, which became the foundation of many programming languages nowadays. And Turing proved it independently using the idea of Turing machine, which became the basis of modern complexity and computability theory. And what I heard is, I think Church did the proof before Turing, but that was like 1930s where people, cannot really use internet, so they didn't really know the result of each other. But Church became aware of Turing's work. So Church invited Turing after Turing proved this. And then later, Turing went to Princeton and then became a PhD student of Church and worked on work with the Church on his thesis. So I think that Turing didn't really need PhD at the time, but he just wanted to spend time with the Church. So he spent some years in the US with the Church. So all this story tells us, initially logic started with a formalization of valid or correct arguments. It gradually moved to the more, to solve the problems of laying solid foundation of mathematics, but and then that objective was not really realized well. But then after this, in a sense, of failure, people turned their perspective on the logic from a different angle. So in particular, the applications of this logic in computer science start to appear, and then it start to, in a sense, dominate many researches on logic. So here are the one examples of Claude Shannon. He did many works, including entropy that appears in maybe machine learning and many other areas. So one of the work that Shannon did was that he showed how to use electric circuits to implement Boolean functions. That became the basis of modern computers. And then another things that happens is the work by John Robinson. So what Robinson came up with the so-called resolution and unification. They became the basis of automated reasoning. And then modern set solver or logic programming, some computation based on logic, they exploit Robinson's result in one way or another. And as I said, this is just a starting point. And then from this starting point, logic start to be used in computer science, more and more. So nowadays, we can see the applications of a logic in many different areas, hardware design, and then as well as, I'm not sure whether you heard about use of logic in database theory and the so-called deductive database and the design of query language and so on. They are all based on some form of logic or analysis of logic. So in fact, one of the major theoretical database conferences called POS, and many papers in POS are about some form of logic. Automated verifications are crucially rely on logic. They use, many of these automated verification tools are based on set solver, which are automatic way of proving or disproving some statements in propositional logic. And knowledge representation, it's not so much popular nowadays, but you might have heard about so-called semantic web. And then the idea is to express some knowledge explicitly using graph, but really behind the graph, what's really going on is some form of a logic called description logic. Programming language theory is also affected hugely by logic. In particular, the so-called type theory, a branch of logic called proof theory, influenced the design of functional languages and type systems in programming language theory. Complexity theory, there is also kind of aspects of complexity theory or some sub-area of complexity theory called descriptive complexity. And they use some tool, they try to analyze the complexity of many problems using this various restricted version of logics. constraint satisfaction problems are studied by algorithm people, and they are very much related to the logic. I mean, you can view them as design of solvers for logical statements. Okay. So there are many applications of logic in computer science, and we are not going to talk about any of these in particular throughout this course. Our focus is more on the foundational aspects of the logic, but we are not really studying logic from, I mean, this is not a logic course from mathematics. So our perspective will be very much computational. So we will ask, if you study about some subfragment of, say, propositional logic, we're gonna ask whether we can come up with some efficient solver or efficient satisfiability checkers for that particular fragment and so on. Okay. So now let me give you, I mean, so some applications of computational logic, I mean, so some other story, which is an applications of computational logic in mathematics and computer science and philosophy. So this is a one which you may not heard about before. So this is one application of set solver, which is automated verifier for propositional logic. So this is a mathematical problem, so-called error-Dodge discrepancy conjecture. And what that conjecture say is that for any natural number C, for any infinite sequence of +1 and -1, I mean, you can always find, this is something called arithmetic progression. You can always find, in a sense, equally spaced subsequence whose sum, absolute value of whose sum is greater than C. So for example, suppose I pick this one, I mean, this sequence as, use this sequence. It's very, okay, 1, 2, and then that 2. This is better. So suppose we have a sequence 1, and sorry about this, somehow. Okay. So we have a 1 + 1 and a +1 -1 +1 -1 -1 +1 -1 -1 -1 +1 -1 -1 -1 -1 and so on. So suppose we have a sequence like this. So it's just, I mean, the needle, I think Selman asked what the title actually means. So needle means there are many, many possibilities. So finding a needle means among so many possibilities, we want to find one case which satisfies some property. Okay. So that's what this title actually means. So for this discrepancy conjecture, say something like this. Suppose we have a sequence like this. Then suppose we pick C is equal to 5. And then the conjecture says there must exist subsequence equally spaced, which doesn't have to start from the beginning, and whose sum is going to be greater than equal to 5, I mean, greater than 5. Let's use 4. So how we can find such a subsequence? And in this case, we can find the subsequence. We pick this second element, -1, and then we jump twice and pick. So okay. So, and then we jump twice and pick this element, jump twice, pick this element, jump twice, pick this element. So it's a subsequence equally spaced. So we, sorry, jump 2 steps at a time, but they are all minus and there are 5 elements. So the sum of these -1, another -1, -1, -1, -1 is going to be 5. So it's going to be example that that is inconsistent with this statement. Okay, and the statement said this happens for all sequence of +1, -1, as well as all number C. That's because our sequence is infinite. So, okay. And then around 1993, what's known about this conjecture is that people knew if C is equal to 1, we can find, this conjecture is true. But they didn't really know if the conjecture is true when C is equal to 2 or more. So I think around 2009, there was some so-called many polymath projects, which is people joined, forces together through internet, and they try to solve some particular math problems by communicating over the internet. So this Erdős discrepancy conjecture for the case of C is equal to 2 is considered as one suitable candidate for doing so. So people launched an attack on this problem together. Lots of people and famous people like Terence Tao and a few others, they joined forces. But the project was not really a success. But so here the quote that you see on the screen reflect the sentiment that people felt after the project. They said, they tried all sorts of, they searched the various counterexamples, but then it turns out there are so many examples that they have to consider, so that it's impossible to come up with an appropriate solution. To solve this problem just by searching. But it turns out if you do a bit more clever, you can solve this by searching, especially using one of the automated theorem prover for propositional logic or set solver. So Konev and Lisica from the University of Liverpool, perhaps, they solved the case, this Erdős discrepancy conjecture for the case C is equal to 2 using set solver. What they did was that if for any sequence of length 1161, any sequence contains the subsequence satisfying the property claimed by Erdős discrepancy conjecture for C is equal to 2. In other words, it contains subsequence whose subsequence with equally spaced, whose sum is absolute value of the sum is greater than equal to 2, or 3 or more. Okay. And their proof was huge. So it's in a sense big success. They used the set solver to solve the open problems in mathematics. But their proof was huge. The proof that if you record the proof, it's going to be 13 gigabytes. Okay, and later, actually, the Terence Tao revisited these problems, and he solved this problem completely for arbitrary C. So, in some sense, the proof by the machine, the automated proof by machine, didn't really live long, but it illustrates the point that the modern set solvers are so powerful that it can be used to discover something new in mathematics. And modern set solvers can be understood as automated theorem prover in logic, which we're going to study in this course. This is another example from this time from computer science. So there is something called sorting network. Okay, so what sorting network does is that it takes sequence of 0 and 1. So what you see on the left-hand side. So this is the input of the sorting network. And then what you see on the right-hand side is the output of the sorting network. And each of the connection like this, what it says is that it takes inputs from the two input wires and compare them and put the one larger to the top, put one smaller to the bottom. So in this case, input is 0 and 1, so the output is going to be 0 and 1. So that the question is, given sequence of 0 and 1, can we come up with the smallest sorting network that's going to sort any sequence of 0 and 1? Okay. And then Knuth asked this question, and Knuth and Floyd came up with a solution for the case when n is equal to 1 to 8. In other words, the number of input is 1 or up to 8, then input wires are 8, then they have a solution, so they come up with the optimal depth, but they didn't know the answer when n is equal to 11 up to 16. And then some students from Oxford, they came up with a solution for them by encoding the problem into set solver. Okay. So here's the solution they found using by the encoding. They proved that, okay, so I want this to disappear. Yeah, they found the solution for n is equal to 10, 11, up to 16. So here's some different examples. This time it's not an application of automated theorem prover for propositional logic. In other words, a set solver. This time it's an interactive theorem prover, and in also the area in philosophy. So Leibniz, he did quite a bit of work in science, but also did quite a bit of work in philosophy. And one of the things he did was he tried to come up with a proof for the existence of a God. So there's some scientists formalize the Leibniz system in some interactive theorem prover called Isabelle HOL in a logic, and then they showed that Leibniz reasoning is correct under some assumption, under certain interpretation of his informal reasoning steps. Okay. So I mean, this may or may not interest you, but the point I'm making is that the study about, well, maybe computational study of logic has an influence not just in science but in art and in the non-science areas. But there are more interesting things in this interactive theorem proving, which I want to mention. There is one thing is called COC. This is some interactive theorem proving. The other one, well-known one, is called the LIN. And people use a COC to prove, come up with prove the correctness of, say, software systems or some algorithms and so on, or also some mathematical statements. So COC theorem prover has been used to formalize, say, the proof of four-color theorem, and then also proof of some classification theorem of finite groups in mathematics, as well as proof of compiler correctness and so on. So, and for the LIN, so it's a bit similar to COC, but perhaps has a more automation built in. And then one interesting thing about LIN is that there is a top-notch mathematician called Kevin Buzzard. I think he was a student of Richard Taylor, who was a student of Andrew Wiles, and Taylor and Wiles made a big contribution to the proof of Fermat's last theorem. So Kevin Buzzard is a well-known number theorist, but at some point he switched into formalization of math. So now he's using LIN theorem prover to formalize the entire undergrad mathematics course, as well as research level mathematics. So one of the things, so he said, if you are interested, you can just Google Kevin Buzzard and LIN, then you will find various talks by Kevin. And then one of the things he said was that he and some of his undergrad students at Imperial, they formalized, I think, the first 2 years of mathematics course. And other things they did was there is something called perfectoid. Perfect. So this is the work by Schultz, who got Fields Medal last year, in the past ICM. And then this is kind of one of the most fancy or most popular mathematics that people study. And then Kevin and his colleagues formalized this perfectoid inside the LIN theorem prover, so that people do formal reasoning about perfectoids. So there are some interesting developments of new types of formalization of math. They care a lot less about the foundational questions, but they want to formalize modern mathematics or research level mathematics in the theorem prover, partly because what I heard, let me just digress a little bit and say it's Kevin's story. What I heard from this Buzard story is that the research level mathematics, even like a master level mathematics, people have there are no problems of understanding and kind of making sure, they're just accepting them, they are true because it's checked by many people in the world. But the really PhD level mathematics, in some cases, there are only a handful of people who knows why certain statements are true. If they die, it's a big problem because nobody knows this. Or there are only very few experts who truly understand the proofs of certain statements. So Buzard said, it's not it's a bit dangerous to continue to do this type of research level mathematics by relying on so few people in the world. So he want to, in a sense, formalize mathematics so that we don't have to rely on, when we talk about the truth of certain statements, we don't have to rely on these people. And it is also true, he said, there are many cases, not many, but some cases where well-known, well-accepted statements turn out to be false. So I think in one of his talks, he gave two papers. One paper says certain statement A is true, and some different paper said the same statement is false, and that kind of thing can happen because proofs are so complicated at the research level. Okay. So anyhow, so this logic is also used in a new way to formalize mathematics nowadays. Okay. Okay, so that's some kind of high-level story about logic and its applications in mathematics, computer science, and philosophy. And then I'm gonna tell you a little bit about what this course is about, and then also tell you how we're gonna run this course. So as I said, of course, is focused on foundations of logic. And in particular, we're gonna focus on computational aspects, which means that we will study some deep theoretical results such as compactness theorem, but the reason we study them is not because this compactness theorem is cool. Instead, we're gonna use these theorems to think about algorithms or semi-algorithms for checking certain statements in logic is true or not. Okay. So we also look at various computability and algorithm questions, and the course is based on the course materials by Professor James Worrell and Dr. Christopher Haas at Oxford and UCL. So here's a bit more detailed picture about topics that we're gonna cover. So I don't expect you to look and understand what's going on, but let me just give you some kind of big overview about all these topics. Some of the topics, for instance, propositional logics, compactness theorem, and so on, they're gonna be about the very basics. So we will study the syntax and semantics of propositional logic, first order logic, and then we're also gonna study so-called the compactness theorem. And this compactness theorem, they are not talked about often in the logic course in some places, but from what I hear, from especially someone who majors in model theory, they say compactness theorem is one of the most important results in logic, because that's really say logic is finitary. We are really constructing things in finite means. And for our application, they will also play an important role because they're gonna allow us to have a decision procedure, and not decision, but semi-algorithm. Also, throughout the course, we will study a few algorithms and semi-algorithms. So we will study polynomial time algorithms for some subfragments of propositional logic, such as Horn clauses, two-set clauses, and XOR clauses. Horn formulas, two-set formulas, and XOR formulas. And we will also study techniques called resolutions and DPL algorithms that combines many of the ideas together. First order logic, we'll study unification resolution and quantifier elimination. They are all related to either algorithms or semi-algorithms for checking validity or satisfiability of first order logic formulas. So they are related to automated theorem approval. And we also look at computability and complexity questions. So we will, I don't think we will show the set problem is NP complete, but we're gonna use the set problem is the NP completeness of set problem. And also for some, the restricted propositional logic formulas such as Horn, will show that our algorithm has a polynomial time. And for first order logic, we'll show undecidability of satisfiability questions, and as well as semi-decidability of some other types of question. And we will look at so-called logical theories, which are some special instances of first order logic where we can decide satisfiability. So we will look at some computability and complexity questions of various fragments of logic in this course. Okay, so that's a big picture about the course, and here's, in a sense, the most important part of the lecture today, which is practicality, how we're gonna run this course. So I strongly encourage you to look at the course webpage, which is set up in the GitHub, as well as check the announcement and Q&A done by me and maybe TAs. And so there are quite a few announcements and some postings in Q&A boards in KLMS. And this webpage and the KLMS will contain essentially all the materials that you need to study about this course or follow this course. Lecture notes, especially look at the course webpage. It contains the lecture notes, slides, homework, not yet homeworks, but also the recorded lectures. They are all available in the course webpage. Not today's lecture, but other lectures we're going to use. And KLMS is the main kind of main medium for announcing important things about this course, also interacting with you through the Q&A. Now, here are just some unusual bit about this course. Today it's more like just normal online lectures, but from the next week, things will be very different, okay? I'm not going to go through the lectures. Instead, what I ask you to do is to watch videos, with video lectures, which are the recordings of my lectures last year, okay? And then if you go to the course webpage, you can see the link to those recorded videos that, which are available in the YouTube. And course webpage give you a schedule, so as well as a link to those videos. So it tells you which videos we expect you to watch in each week, and then what are the links, how you can access these videos. Now the real-time Zoom meetings will be dedicated for Q&A and oral test. So we don't usually, so on Monday, we don't normally meet, but Wednesday we will meet, except for the national holidays. Wednesday sessions will be our Q&A sessions. So you will find my postings in the Q&A board in KLMS. And then I have a posting for each Q&A session. So I think maybe 11 or 12 or more the postings there. If you want to discuss about certain questions related to the videos that you watched in the week, then you can write those questions as replies those my postings in the Q&A board. Then I will look at these questions on Tuesday morning, which means that if you put those questions by midnight on Monday, or maybe very, very early, maybe 1 a.m. or 2 a.m. in Tuesday, then I will look at them. I will pick the one that are important or interesting, and then I will discuss about them on the Wednesday real-time Zoom sessions. Information about real-time Zoom sessions are available in KLMS. Now, the last bit is also very important. There will be, we are not going to have a midterm or final, but there will be oral test. So it's something which I never tried. I don't know how it's going to work, but I thought it's worth trying. So there will be 4 Zoom oral tests. They will happen on Monday. So the dates are fixed. So you have to attend them. If you don't attend, you get 0. And I'm going to tell you more about how these oral tests will be run. Okay. And teaching step, I'm Hong Seok, and I'm giving lectures. My office hours is going to be on Monday from 6 to 7 p.m. And Zoom ID and password, they are all available in KLMS. And there are 2 TAs, Hyungjin and then Jungmin. And they are, I think they put their office hours in the KLMS as well. So, I mean, somehow, when I teach the same course last year, not many students ask for help in my office hours. So, I mean, my office hour is reserved for, office hours are reserved for helping you. So if you have, even if you feel like you have a dumb question, you can come and then discuss about them. Okay. And the evaluation will be based on these 4 items. The first is homework. There will be 4 problem sheets, and they will account for the 40% of the total marks of the course. There will be 4 Zoom oral tests, okay? And they will account for the 30%. And the Zoom oral test will happen in those 4 days. 2 of them, like April 19th and June 14th, they are in the middle of either midterm or final exam. The other 2 are just normal non-exam periods. Okay. And there will be a programming projects and a short report about what you did in the project that will account for the 20%. It's going to be implementation of a self-solver based on the DPL algorithm with closed learning. And the last component is a critical survey on a particular topic, which is called MaxSet. So this is an optimization version of self-solver, which also performs extremely well in some cases. For instance, when I did in my research, I used MaxSet solver to solve some problem which have about 20 million variables and 40 million constraints. So, I mean, it's something which is work really well, and I want you to have a survey about this and understand what kind of algorithms are used, and as well as I want you to think about how, want to think about how you can improve existing algorithm or how you can do something new about these algorithms, these MaxSet solvers. Okay, so the unusual part of this course is oral test. So we're gonna have a 4 in-class randomized oral test. 2, which happens during non-exam period, will go from 9 to 10:15. 2 that happens during the exam period, that will go from 9 to 10:30. Okay, and they will all held in Zoom, and it's a randomized. So what I do is that I will randomly call the names of students. If students, just is absent, that students will get 0. Okay. And then if the students answer the question well, then that students will get plus point a little bit. And the students doesn't perform well, the students will get a minus. Okay. And I'm expecting you to answer questions using microphones. So at least for those 4 days, I want you to be, a bit like doing some form of interview in some companies or maybe in the graduate schools and so on. And also for these exams, at some point, either during the attendance check or when they answer questions, we may ask you to turn on cameras. Okay. Officially, the attendance check will happen 9:30. If students miss the attendance check, they will get 0. But unfortunately, some unfortunate students who get called before this attendance check but is absent and join later, they will get 0. So make sure that, it's a bit random. So if you feel like, you're lucky, then you can come a bit late, then you can go to the attendance. You will have no problem of getting full marks in terms of attendance. But if you feel like you're a little bit conservative, you may be better to come a bit early. Likely, we're gonna start in maybe 5 past instead of 9 or 9. we will have a 9:05 to accommodate some students just late for some few minutes. And if you go to the course webpage, you'll find more information about them. So, and each of the oral tests, the scope of the oral test is already announced. So if you go to the course webpage, then you will see that which topics will be covered in each of these oral tests. Okay, the critical survey will be on the Max Sobers. I don't expect you to write a very long survey, so at most 3 pages, excluding bibliography. And then the submission deadline is, it's essentially midnight of 3rd of May, 2021. It's a Monday. And then submission box is already available in the KLMS. So if you finish very early, like in April, you can submit it there. It's already there in the KLMS. And then one important bit is that we will be very strict about plagiarism. So some students, especially undergraduate students, are not very trained or didn't really hear very much about the danger of plagiarism. If you just cut and paste from some text, either in Wikipedia, one in textbook, that's regarded as a plagiarism. If you want to use some contents from some material, you have to rewrite it your own, or you have to, if it's a direct quote, you have to explicitly say this is a direct quote. Okay. So make sure that you are, you follow the rules again, about the standard rules about how you should avoid plagiarism. And that brings us to this honor code. So we're gonna adopt a very strict policy for handling violation of standard honor code. If a student is found to cheat tests or copy answers from or code from friends or other sources, the students will get F. And in the past, we adopted the same policy for multiple courses. There was one case where students found to cheat, and then that students got F as a result. So the best way to study the course is to look at the lecture note. The lecture notes are written mostly, it's written by my colleagues, the Professor Worrell and Christopher Haas, the Dr. Haas. They are the ones, actually Worrell is the one who wrote these lecture notes. I revised a little bit, fixed maybe a minor typos here and there, but they are very good. If you just look at the lecture note, you can understand pretty much everything that's going on in the course. So lecture notes, slides are the main sources of information in this course. If you want to know more about the computational side of logic, these 2 books that I highlight in the slide, they are also quite good. The book by Aaron Bradley, the Calculus of Computation, it's a book that emphasizes the use of logic in verification. And it's an excellent book. And Logic in Computer Science, that's another very well-known popular books of logics, aimed for computer science students. And then there are further books that are mentioned in the course webpage. I highlighted the Logic Comics because it's fun. If you haven't read this book, it's a comic book, and you may like it. It describes the history of logic, the one that part of it which I covered in a few slides before. If you want to know more kind of hardcore materials, the second book is also, I didn't read it, but second book is also regarded as very important. Sermon, yes, the compactness, we are describing it in a bit different way, but it's essentially the same thing. So it's essentially what the compactness that I'm gonna, so Sermon asked the definition of compactness is gonna be same as the one used in topology. Yes, that's the case. And in some sense, what the compactness theorem that I'm gonna talk about is instance of so-called Tikhonov theorem in topology. So it's a product of product topology. It's a property of our product topology. So this second book is highly recommended. My friends who work on very highly. He said he learned about all the tricks on automated theorem proving from this second book. So if you want to really understand in and out of the automated theorem proving, I recommend you to have a look at it. Although I didn't mention it here, if you are interested in the really all the minor details of set solver, Knuth have a book on set solver. This one of the kind of volumes on the art of computer programming that Knuth is writing is about set solver. So if you, are interested, then you can have a look at that book. That describes not just the high-level algorithms, but also all sorts of implementation tricks for having the efficient set solver. Okay, so this is the last slide. Throughout the course, we're gonna use quite a bit of mathematics. Okay, so I expect you to be able to prove mathematical state, read and write proofs in mathematics. Also, I expect you to be at least not afraid of looking at some statement like the one that you see on the screen. The first statement is essentially about Markov inequality. We're gonna use Markov inequality, and here I'm asking you to prove this Markov inequality. So some of the students, whenever they see probability, they just turned off, but make sure that you are not, you are tolerant to these type of statements in this before deciding to take this course. The second, we will talk quite a bit about the complexity analysis. For instance, what's going to be the computational complexity for solving system of linear equations using Gaussian elimination. I want you to be able to answer this question. And we will use quite a bit of concepts from the complexity theory or algorithm course, such as NP, NP-complete, regular, recursively enumerable. If you don't know, I know that some of the math students in the course haven't heard about these concepts before. If you can look at Google these concepts, and by looking at the Wikipedia page, you can catch up these concepts, that's okay. But if you find doing so is very difficult for you, and just digesting these new concepts and using them is difficult, then maybe it's better to reconsider taking this course. And so there are a few statements, like the next two are about this regular language. It's a formal language theory. The later part of the course, we're gonna use this statement, which is if you have some subsets of sequences, and that subset and each complement are recursively enumerable, then L is recursive. And this is some of the result from the very simple result from computability theory. And if you are aware of this, great. If you don't know, but ready to learn about this, that's also fine. But if you feel like, oh, I don't really like this type of statements, again, this is not the right course for you. And then the last bit is about the proof it's a program related to the program verification. And in fact, when we discuss about the algorithms for the Horn formulas and two set formulas, two CNF formulas, we will argue the correctness of these algorithms using these rules, the principles of so-called loop invariance. So the last question is about prove this correctness of this program using loop invariant. Again, if you are happy to Google loop invariant and find out what it is, and then just learn about it and use it in our setup, then that's good. But if you don't like to do so, then maybe it's better to think again about whether this is the right course for you. Okay, so that's it for today. So we are not going to meet next Monday, but I'm expecting you to watch videos which are available in YouTube. The links, which videos to watch, the links to the videos will be available in the course webpage. Okay, so that's it for today. I'm gonna stay here until maybe 5 to 10 more minutes. So if you have any questions, you can ask. Okay, so thank you very much.